Okay, so I'll go ahead and get started. So today's lecture is, let's see, I've given it a title, From Atoms to the Cosmos, but basically what I want to talk today about is the connection, or at least starting to talk about the connection between the microscopic world and the cosmos on the grandest scales. And it turns out that there's a lot of interesting connections there that you'll see again and again in cosmology. But today I'm just going to talk about it primarily in terms of energy generation in the stars. And I'm going to use it as an opportunity to talk a little bit about the microscopic world and the structure of atoms, primarily because I understand that this might be the only science course that some people here take, and I'd like to at least introduce those concepts a little bit. Now, last time I talked about this question of what powers the sun, and I told you about this story where there was this sort of debate between Lord Kelvin and Darwin about what powered the sun. And does anyone remember why was it that Lord Kelvin got the answer wrong, primarily? Yeah?
He said that the thing that powers the sun is gravitational.
Right. His idea was that the origin of what powered the sun was gravity. And what the debate about was actually the age of the sun. And he made the point that, well, look, if gravitational energy is what's powering the sun, if you're trying to extract all of that energy that the sun is spitting out from gravitational energy, then there can't be enough energy there for the sun to live very long. So 30 million years was the number that he got. Whereas Darwin needed a number greater than 300 million years in order for natural selection to work. So what Lord Kelvin didn't understand is that there's yet another energy source. And that energy source, in some sense, is nuclear energy. And it derives its energy basically from this equation, E equals mc squared. So the basic idea is you take a little bit of mass and turn it into pure energy. And if you can do that, that's so efficient that you can effectively power the sun for billions of years. A little bit more detail about where that energy comes from is effectively what you're doing is you're taking 4 hydrogen nuclei, and that's 4 protons, and by some process you're generating a helium nucleus out of that. And because a helium nucleus is in the end is somewhat lighter than a hydrogen nucleus by a little bit, when you do that process, you actually liberate energy. And so that's the idea. Now, if you recall, we actually put some numbers into the E equals mc squared equation to figure out what kind of energy scale we're talking about. Okay, and so you can ask the question, in principle, how much mass energy, how much rest energy is there in anything that has a mass of 1 gram? So the way you do that is you stick in 1 gram for m, and then you stick in the speed of light for c and square it. And when you multiply all that out, what you find is that you get 9 times 10 to the 13 joules. Okay, and joules is a standard unit of energy. And this is a lot of energy. Okay, and I'll give you another example of how much energy that is in a second. But what this means is that you can then, if you want to, if you're interested in understanding how much mass energy something has, you can actually just use this equation. Okay, so if you have something that has 1 gram of energy, or 1 gram of mass, you stick it into this parentheses here for m, and you see that the grams will cancel and you get 9 times 10 to the 13 joules. But because this whole thing is proportional to mass, you could stick in 100 grams instead, and you get the same answer that I got here, it's just you would multiply this whole thing by 100. And so you see that by sticking it in the parentheses here. All right? So what I'm telling you is, there's a very simple version of the E equals mc squared equation that we've just derived, which is this. So you don't have to go through multiplying the speed of light squared every time. And so if I give you a problem, for example, on, say, a midterm, where I ask you how much mass energy is in a kilogram of lead, you can put a kilogram in, so 1,000 grams, and get an answer out. Okay? So let's do another example of this. let's say the question was, how much mass energy is locked up in 20 nickels? So imagine you have a stack of 20 nickels. 20 nickels weighs something like 100 grams. So if I want to figure that out, I just take 100 grams. I take this equation that I just derived. I stick 100 grams in for m, multiply it through, and then you get 9 times 10 to the 15 joules. Is that clear? Any questions about that? So now I can say, all right, well, how much energy is that really? So what does that mean in some other terms? Okay. Well, let's compare that to how much energy you can contract via combustion, like with an internal combustion engine. In principle, how much energy can you extract from a gallon of oil? So it turns out that with a gallon of oil, you can get about 10 to the 8 joules of energy. Okay? And so to put this kind of number in perspective, we've got 9 times 10 to the 15 joules of pure mass energy in a stack of nickels. But in an entire gallon of oil, if you want to burn it and make your car run, you can only extract about 10 to the 8 joules. So there's a huge difference there of more than 7 orders of magnitude, almost 8 orders of magnitude. So let's say we want to understand a bit more what that means. So it turns out that in a typical American who tends to drive a car a lot will use about 2,500 gallons of oil in a year. So the amount of energy it takes to, for a typical American to do all the driving they're going to do over the course of a year is about 3 times 10 to the 11 joules. So we're still not actually up to that number. And in fact, it turns out if you take the energy, the mass energy contained in this stack of nickels, and compare it to all of the energy you use driving around in a year, that's 36,000 times. So what that basically means is that there's enough mass energy in 20 nickels to power the driving habits of 36,000 people for a year. So you can see there that in principle, this source of nuclear power, if you could tap into it, there's a lot of power there. There's a lot of energy in principle that's tapped in, that's locked in mass. The problem is, of course, that there's not a magic box that you can take something that has some mass, put it in the box, and energy comes out. Okay? If so, that would be nice. That would be very nice. If anyone has such a box, let me know. But in practice, what you really need to do, the processes that actually are able to tap into this mass energy are basically nuclear fusion or nuclear fission. So nuclear fusion or fission. So let me show these little movies again. So nuclear fusion is basically the idea of you take 2 light nuclei, bring them together, and they form a heavier nucleus. That's fusion, so fuse. Okay? And fission is the opposite. You start out with a big, heavy nucleus and shoot something at it, for example, like a proton or something, and the thing will break up into 2 lighter nuclei. So they're 2 very different processes. Now, it turns out that nuclear fusion works because the fused nucleus ends up being lighter, less massive, than the things you stuck together to make it. Okay, so you lose mass and gain energy. But it turns out that that energy gain only works up to a certain nuclei, certain type of nucleus, and I'll talk more about nuclei in a bit. And it turns out that if you're heavier, more massive than an iron nucleus, you don't gain energy by adding stuff to it to build a bigger nucleus. So if you start out with a nucleus that's really big, like say uranium, and break it apart, then it turns out that its products, if you add the sum of the masses of the products together, it's less massive than the thing you started out with. And so you gain energy by breaking it apart. So in principle, you can gain energy by fusing up to a certain point. And then once the nuclei gets really big, you can gain energy by breaking it apart. And at some level, that's just a fact. That's just a property of nature. It's a property of the nuclei of different types of atoms. Are there any questions about that? Yeah.
Do you think one day we'll be able to do this as efficiently as the sun does it?
So the question was, one day will we be able to do nuclear fusion as efficiently as the sun does it? I think it's not even a question of how efficient we do it. It's just, can we do it at all for a cost that's such that it's cost effective? Fusion. Now, we currently do fission, just to clarify, right? So let me say a bit more about this, and I'll return to the question about a reactor. Okay. So nuclear fusion is the thing that happens in stars. Okay. So in the sun, this is what's powering the sun. So you're taking lighter nuclei and eventually building helium, basically. This is also what's used in modern nuclear bombs. So, in fact, we do create nuclear fusion reactions, chain reactions that involve nuclear fusion, and those are used in thermonuclear bombs today. Those are not the first kind of atomic bombs that were invented, but sort of the modern incarnation of atomic bombs. That's what's going on. Now, it turns out that it's easier to build a bomb than it is to build a reactor. Okay? So you can create this reaction and it will just explode. Now, creating a reactor or a usable power plant with this type of technique is quite hard, and I'll talk a bit about why in principle it's hard. So the question you asked me is, do I think that we will ever do this? I don't know. So right now, I mean, there's an old joke about nuclear fusion reactors, and that's that they're always 30 years off. So 30 years ago, people who worked on nuclear fusion said, oh yeah, it's about 30 years off. We're making a lot of progress. We estimate in 30 years we'll be there and we'll have a usable reactor. If you ask someone today, the world expert on nuclear fusion, they are likely to say, yeah, we're definitely getting there, but in about 30 years we're going to have a usable reactor. So that's the joke, that it's always 30 years off. And the thing is, it's hard. So it's a very hard process. And I'll talk a bit later in this lecture about why it's so hard to make this happen. The sun does it. The sun is able to do it because the sun is really massive. And you have to cram all this stuff together to make this thing happen. The problem is, once you cram it together to make it happen, then a lot of energy comes out and the thing explodes. Okay? And so in principle, you don't want to have a bomb for your reactor. You want to have something that you can control and that's stable. How do you hold it, without the walls disintegrating and that kind of stuff? And there's a lot of money being invested in this technology. Now, let's compare that to nuclear fission, where you take big nuclei and break them apart. That's the kind of thing that's being done now with modern nuclear reactors. Okay? So, and in fact, the new generation, the new technology of nuclear reactors is a lot safer and efficient than it was 20, 30 years ago. And this is a really useful and interesting direction to think about for future energy sources on Earth. Because in principle, it does tap into this E equals mc squared energy. But there are decay products. So these big nuclei that break up, okay, almost by their very nature are radioactive, and they're decay products. And the products of this nuclear reaction is also radioactive. There's lots of neutrons and everything. And so the spent fuel from these nuclear reactors is radioactive. And so the issue is, what do you do with this spent fuel, and how do you store it in such a way that it's safe? Okay. Now, in principle, fusion energy is cleaner because the decay, in principle, the products are all very clean thing, or cleaner than the products that you get out of this. They're not these super heavy nuclei that are automatically radioactive. In practice, though, that when you have any process that turns out spitting out neutrons, which is what happens here, that tends to create radioactive stuff too. So it's not like, if you had a fusion reactor, you wouldn't have to worry at all about radioactive stuff, but it wouldn't be as problematic as this. So it's cleaner, in principle, a better technology. Also, you don't have to rely on some rare elements and expensive elements as your fuel. Here you need big, heavy elements which tend to be rare. Here, in principle, your starting point things that you can use to fuse are much lighter and cheaper. Okay. Are there any questions about that? Okay. So now, in order to understand this process, so what I want to do eventually is talk a bit about what's going on in the sun in greater detail than what I've talked about already. But in order to do that, I need to talk a bit about the microscopic world, because I've been talking a bit about atoms and stuff, but I need to sort of back up and talk more about what's going on in the microscopic world. What are the forces that govern interactions between things? So today in physics, we understand that there are it turns out, four forces that govern everything we know that's going on in nature. So there are four called fundamental forces of nature. And they're listed here. So there's the gravitational force, okay, that we're all familiar with. There's the electromagnetic force, which I've already talked about in this course. Then there's something called the strong force and the weak force. And these four forces of nature control all of the phenomenon that we're aware of. And in fact, they can explain everything we've ever observed in nature, these four forces. You have to throw in matter as well, different types of matter, but these four forces explain all the force phenomena that we're aware of on Earth. So the gravitational force, like I said, we know about this. Gravity is responsible for planetary attraction. The gravitational force is what keeps us, grounded on Earth and keep us from floating away, right? It's pulling on us. It's the same Newtonian gravity that I talked about. And in fact, it's responsible for the large-scale structure of the universe. Anything that's going on that affects the motions and forces between things on very large scales, like the scale of the solar system and larger, is certainly governed by gravity. So gravity sets all that. Now, the electromagnetic force is interesting, right? So it's electricity. The electromagnetic force governs all of chemistry, basically. All of chemistry is the electromagnetic force. So that means all of biology is the electromagnetic force. And life, and all that stuff. It doesn't mean we understand how life emerges, but if you break it down to the most fundamental level, all of those interactions that are going on are basically interactions between electrons. And that's the electromagnetic force. The electromagnetic force, so let me back up a little bit. So when you think about forces, what am I saying? So forces are the things that push and pull you, right? So one of the things that's happening right now is I'm standing on this floor. But gravity is pulling me down. So what is stopping me from falling through the floor? Why am I not falling through the floor? Sorry? Because the floor is pushing back on me? Okay, that's a good start. It's a nice way of starting. But how is it pushing back on me? How? What is it doing? What is it? What is the force that's being applied to me? It's not gravity, right? So gravity is pulling me down. Something is pushing me back. Sorry? Well, we call it the normal force. If you take a physics class, that's the label you give it. It's the force that's pushing back. But I mean, like, in some fundamental microscopic way, what is pushing on my feet?
Solid matter.
Solid matter, okay. Is it really solid? That's the question. So if I take a microscope, I'll get you in a second. If I take a microscope and I look carefully at this stuff I'm standing on, is it solid? Yeah.
Well, all the atoms and particles, there's technically a very, very, very small amount of space in between. So technically when you step on top of it, there's a small barrier from the electron cloud that's holding you off of it. So you're technically a small amount of space which different opposite charges.
There we go. Okay. So if you look on a very microscopic scale, what he's saying is you'll see that everything's made of atoms and molecules and stuff, right? And what is an atom? An atom is basically a cloud of electrons. There's a little bit, as I'll talk about later, there's a little nucleus of protons and stuff in the middle, protons and neutrons. But the vast amount of size in an atom is a cloud of electrons. And the electron itself, as far as we can tell, is a point particle, meaning it has no size. So you have an electron that's kind of orbiting around at some distance. But that electron has no size. So what's going on is the electron has an electric charge, a negative electric charge. And the atoms in the bottom of my shoe also have electrons, which have negative electric charges. So when you bring those two electrons together, two negative charges do what? They repel. So what's happening, the reason why we're not falling through the floor is because electrons repel each other. And that's the electromagnetic force. That's the only reason why we don't fall through the floor. That's why when I hit my fist on this, it's solid. Because those electrons are all crammed together, and when I encounter all those other electrons, there's an electromagnetic force that pushes back. In the air, it's a much more diffuse situation, right? So there's electromagnetic forces in the air too, but the atoms are really far apart, so I can take my hand through it and I don't feel it. I mean, I feel a wind, and basically that also comes from the electrons. But it's not as strong, right? They're farther apart, so I can take my hand and wipe through it. So that's what I mean by fundamental forces. It's like the fundamental thing that's doing the pushing. Okay. Now, the next thing on this list is called the strong force. Now, that was great in the microphone, I'm sure. Hi, everybody. So the strong force, remember we talked about the nucleus of an atom. What does a nucleus contain? What's the nucleus of an atom? Protons and neutrons. And they're all stuck together, right? So let's say you've got some atom that's got two protons, and they're all confined together in nucleus. What do those protons want to do because of this? Protons have a what kind of charge? Positive charge, and they both have a positive charge. So two positive charges, what do? They repel. So if you try to take two protons and cram them together like that, like in a nucleus, in principle, because of electromagnetic forces, they just want to fly apart. The strong force is what keeps them bound there. There's another force that takes over. And it only operates on really small length scales, it turns out. Really small length scales, basically the size of a nucleus. And it doesn't operate outside that size scale, it turns out. It's a weird force. But when you get close enough, the strong force grabs those neutrons and protons and holds them together. Okay? And it's very strong. Okay? So over here on this column, I'm talking about the relative strengths of the forces. So if I normalize things so that the strength in some, it doesn't matter what units, just size, the strength of the strong force is 1, the strength of the electromagnetic force is something like 0.01. So the strong force is 100 times stronger than the electromagnetic force, and that's why it wins. That's why it can hold those protons there even though the electromagnetic force wants to send them flying apart. But the other weird thing, like I said, is that the range of the strong force is very short. And what we discovered is that it only operates on very, very close by. And if you take two things and bring them farther apart than that, that strong force doesn't act anymore. That's different than electromagnetism, which is infinite range. If you have a proton over here and an electron over here, and they're infinite and they're really, really, really far apart, they will still feel the tug of each other and start moving towards each other. And it's the same thing with gravity. If I have two massive bodies that are far apart, it doesn't matter how far apart they are, they'll feel a force. It might be a weak force, but they will still feel a force that will want to make them come together. Notice in the scheme of things, gravity is ridiculously weak. So in areas when you can have interactions, electromagnetic interactions will be way more important than gravitational interactions. Okay? So that's why you can build a structure that doesn't just gravitationally contract on itself. Because if you have some, piece of wood or something, it will stay sturdy and not just contract into a small ball or a black hole because of gravitation. because those electrons want to repel each other, and you have some complicated lattice because of electromagnetic forces, say in some kind of material, and that keeps you solid, having finite size. And that's why electromagnetic forces govern basically everything that's going on in our bodies, and not gravity. The strong force doesn't matter that much either in the macro sense for what our bodies are doing, because the size scale where it matters is very, very small. Okay. Now, there's one other type of force that has been discovered, and that's called the weak force. Notice that it's not weaker than gravity, so it's kind of a funny name, but it's weaker than these other two. And its range is also incredibly small, and it's also fairly weak. It's weaker than electromagnetic, which is why it's called weak. The weak force is responsible for radioactive decays. And I'll talk a bit about radioactive decays in a bit, but basically if you have a neutron, turns out, for example, if you have a neutron and you bring it out of a nucleus and just have it sitting there, it will decay after a little while and turn into a proton and spit out. It turns out it'll turn into a proton, spit out an electron as well to keep things neutral, and also something called a neutrino. And that process is governed by this weak interaction. But if you add all these forces together, that explains all the phenomena that we've ever observed on Earth. And there's nothing that we're aware of that defies this, that steps out of this. This explains everything. So it's kind of amazing. Now, one point I want to make, especially in the context of a cosmology course or astrophysics course, gravity is the thing that matters the most. Gravity always wins when you go to large enough scales. All right? So why is that? Does anyone, let's think about it. Why is it that gravity always wins based on this? Now, what I'm saying is you go to large enough scales. So in the first line, I say, gravity is what governs the orbits of the planets, the structure of the solar system, turns out the structure of the galaxy, more or less, and more importantly, the interactions among galaxies on the largest scales in the universe. So why is it that gravity is the thing we care most about on the largest scales? Well, there's there's only 4 forces we have to worry about. There's 2 of these forces that once I go to big enough distances, length scales, that's what I'm talking about, I don't have to worry about them anymore. Which are those 2? Yeah, the strong and the weak, because these things have ranges that are small. So that's very easy. So these I can just eliminate because they have small ranges. Now what about electromagnetic force? It has infinite range, and it's stronger than gravity. So why is it that once I get big enough, the electromagnetic force doesn't matter anymore, and it's only gravity? Yeah?
Is it because there's no matter in between like large bodies in space? Like space is a vacuum, so there's no electromagnetic noise?
Okay. So you say, is it because there's no stuff in between these large bodies, so there's no real electromagnetic activity going on? You're getting there, but what kind of stuff has electromagnetic activity? What kind of stuff? What do you need to have an electric force between 2 things? This is something I haven't really talked about yet, but I just wonder what people... So if I have 2 neutrons, say, neutron here and a neutron here. Do you have an answer? Yeah, what? Yeah.
I was going to say you need charges.
You need charges, exactly. That's where I was going with the neutrons. Right? If you have 2 neutrons, they don't have any charge. So if you put them next to each other, there's no electromagnetic attraction or repulsion between those things. Okay, so you need charges. So the Earth as a whole doesn't have a charge. Every neutron has a proton, basically, right? In this room, it turns out, globally in this room, there's no net charge, which is good, or else we'd get a big shock of static electricity or something. You don't want to build up a charge anywhere, or else then electrons will flow. Okay? That's why you always want to ground your wires and stuff. Okay? You don't want to build up charges. And you don't build up charges. Once everything's all connected, there's equal numbers of neutrons and protons basically, and so there's no net charge. So once you go to a really big scale, everything's neutral. And so since you need charges, electromagnetic forces acts on charges. Once you go to the scale of a solar system, there's no net charge, and gravity will start to win. So the universe is neutral on average, it turns out, which is interesting in and of itself. And so that means on the largest scales, the structure is governed by gravity. And that's why Newton could understand the motion of the moon and the motion of the Earth around the sun and all of that stuff using only the law of gravity without understanding electricity or any of these other things. Okay, so now let's go back down to very small scales where gravity doesn't matter now. So if we get to small enough scales, gravity doesn't matter. The world is governed by other types of forces. So what is an atom? I said this before, but an atom is a nucleus surrounded by a nucleus of protons and neutrons surrounded by electrons. Okay? Now, a typical size of an atom is something called an angstrom. An angstrom is about 10 to the minus 10 meters. Right? So that's very small. And a nucleus, the nucleus of the atom, is something like 10 to the minus 14 meters or smaller for even smaller nuclei. Okay? So that's a huge size difference. So you have the nucleus, this tiny little thing, and then an atom, and then the electrons of that nucleus are 10 to the 4 times farther away than the size of the nuclei. So if we put that in perspective, if the nucleus were the size of a marble, the atom would be the size of a football field. So thinking of atoms as solid things, as we were thinking about in the beginning, is totally wrong. Atoms are mostly empty. They're like marbles surrounded by, with electrons orbiting around them at a distance between like 50 yards or something. So they're mostly these big empty things. But the thing that gives them what seems like solid structure is the fact that there's this electrical force that kind of gives them that shape and that repulsion. So the proton in the nucleus attracts that electron, or ever how many protons there are in the nucleus, attract those electrons and keep them orbiting around, keep them bound. The size of atoms, the chemical reactions of those atoms, the spectra that we were talking about before, those spectral lines, all of that stuff is determined by the electrons. It's the electrons that do everything. Exchanging electrons, sharing electrons in bonds, all that kind of stuff is governed by electrons. And atoms want to be neutral. Yeah?
If I sat on a chair and it broke,
Yeah.
that just mean I have more repulsive electrons than...
No, if you sit on a chair and it breaks, that means you have so much mass that the Earth is pulling down, okay? And those bonds, although they're strong, they're not strong enough to overcome that gravitational force that you're basically applying on the seat to break it. Okay? And so that's why the floor has to have some strength to resist against gravity. Okay? Okay. So, but the point here, the point I was making here was just that atoms basically want to be neutral. If you have an atom that's not neutral, that say has more protons than an electron, it will then have a force to want to attract another electron, and eventually it's going to grab one. Unless conditions are such that it can't hang on to it. It might be if it's way too hot, so you have too much energy of motion, you keep knocking electrons off. But all things being equal, atoms want to be neutral. So these are just schematics, so you sort of see what I'm talking about with atoms. There's protons and neutrons. The protons and neutrons roughly have the same mass. Roughly. They're not exactly the same mass. But they're roughly the same mass. And it's about 1,800 times the electron's mass. So they're much heavier than the electron, much more massive than the electron. Okay? Protons have 1 unit of positive charge, we say, and neutrons have no charge, electromagnetic charge. They live in the nucleus, and the electron has 1 negative charge, and they're always in. If you have an atom that's neutral, there's an equal number of protons and electrons. Now, it's possible that you can have electrons that are, you can have atoms that are missing some electrons. Those things are called ions. So if you take out an electron, and now you have an atom with a net charge, a net positive charge, it's called an ion. Okay? And then these different types of ions have different labels. I just wanted to make sure you've seen this somewhere, so I'm just mentioning it. The word ion means you have an atom, and you're missing missing 1 or more electrons. Those are different ions. So it's not that you can't have situations like that. It's just that when you have something like that, then those ions are trying their best to grab an electron to get themselves neutral again. So what is it that defines an element on the periodic table? Yeah. Yes, it's the number of protons. So if I tell you I have some iron, okay, that tells you how many protons is in the nucleus of the thing I'm talking about. It does not necessarily tell you how many neutrons you have. Okay? So elements are defined by the number of protons. You have 1 proton, you're talking about hydrogen. 2 protons, you're talking about helium, okay, etc. Lithium is 3 protons, oxygen has 8 protons, iron is 26, uranium is 92, etc. Now, typically in a nucleus, you'll have 1 to 2 neutrons per proton. And in some way, they kind of act like glue. They're sort of the glue that gets the strong force kind of going and operating to keep them all stuck together there. All right. Now, but even, hydrogen has different isotopes. So that's what sorry, I haven't defined that yet. So an isotope is you have a certain atom, which is number of protons. The isotope tells you how many neutrons you have. That's what the word isotope is. All right? So isotopes are the same element, you just have different numbers of neutrons. So for example, here are 3 isotopes of hydrogen. Here you have hydrogen that has no extra neutron at all. It's just proton in the nucleus. Here you have hydrogen that also has a neutron. That's called deuterium. And here you have a hydrogen that has 2 neutrons. So a total of 3 things in the nucleus. That's H3. That's called tritium. Okay? Similarly, helium has different isotopes. Here's helium-3 and helium-4. Are there any questions about that? I'm not going to test you on this terminology, all right? But I just want to make sure you've kind of seen it before. You hear these words used all the time just in common language. And so in case you haven't had these courses recently, I just want to remind you what this is. Now, I am going to talk about it when I talk about energy sources in the stars, so it's not completely irrelevant. But I'm just telling you, I don't care about the names. I just want to make sure you're familiar with this. Yeah?
Is it possible for an atom to have a net negative charge?
A net negative charge. Is it possible for an atom to have a net negative charge? Yeah, I think for a very short amount of time, in principle, you could have, it wouldn't be bound to it, but probably in a complex system, you can somehow associate extra negative charge with an area, at least near an atom. Okay, I don't know if you would call it bound to the atom or not, but there are certain regions where you definitely have net negative charges. It would be hard to configure an atom just free floating in space that had just an extra electron somehow bound to it. I think that would be a hard thing to set up. Now, this idea of isotopes, turns out, matters for things like radioactivity. Because certain isotopes of atoms are radioactive, that means they're prone to decay. And certain other ones are not. Okay? Now, you keep track of the isotope and the number of protons and neutrons when you look at the periodic table by using superscripts and subscripts, just in case you haven't seen this before. The atomic number of an element basically tells you what kind of element it is. It's the number of protons. It goes down here, it's in red. The mass number is just you add up how many things are in the nucleus. You add up all the protons and the neutrons, and that's the bigger number. For example, for uranium, this is 238. All right? And then the number of neutrons is just then the mass number minus the atomic number. So it's whatever you need to add to the number of protons to get the mass of the nucleus in units of nucleons. Okay? So sometimes nuclei are not stable. And in particular, usually it's the bigger ones, the ones you're just cramming a lot of neutrons in there and you've just got big complicated nuclei. Usually oftentimes those are the ones that are not stable and they decay over some time. If you just sit them there, they'll decay. Okay? And if you have such an isotope that's prone to decay, you say it's radioactive. It's spitting stuff out as it decays. Okay? And that's the reason why radioactive stuff is problematic, okay, is typically you have a bunch of things spitting out of it. And when those things hit your body, sometimes it's not good. Or sometimes those decay products wind up in your water or something, and you don't want to drink that. So uranium-238, is the primary source of radioactivity on Earth. The Earth is radioactive. You can measure those radioactive products coming off the Earth. And globally, it's this uranium-238 that's the primary source, although there are other sources. Bananas are radioactive, turns out. So there's different kinds of emission you can have in this radioactive products. You can have either an alpha particle, a beta particle, or a gamma particle. Now, it's historical why they have these names. And they have these names because at the time this kind of radiation was discovered, they didn't know what was going on. They just knew different things were coming out. So they gave them these names. Now we understand sort of at a microphysical level what these things are. All right? So alpha particles are just helium nuclei, it turns out. It's a common thing that's spit out of radioactive things. So it's 2 protons and 2 neutrons together in a nucleus. Oftentimes, these alpha particles will come out of radioactive objects. A beta particle is just an electron. And a gamma particle is just an electron. It's a high energy electron, a gamma ray. So people talk about radioactive gamma rays. It's an electron that comes out of some kind of decay process, some kind of atomic decay process. It's like a daughter particle. Here's an example of 3 different types of carbon. Only one of them decays, carbon-14. So carbon-14 is radioactive and decays. So what will happen if you have a carbon-14 atom and you just let it sit there for about 6,000 years, eventually it will decay. It's not stable. It's not super stable. And what I mean by it will decay is it will spit out an electron and a neutrino, and one of its neutrons will turn into a proton. So it has this neutron. One of the neutrons decays, turns into a proton. Electron shoots out as part of that process, and you end up with nitrogen. So in principle then, if you can measure ratios of carbon and nitrogen in objects, that's a way to date it. That's a way to find an age date for something. Because we know how long it takes on average for one carbon atom to decay into nitrogen. One carbon-14 to decay into nitrogen-14. So carbon dating, I just thought I would mention this to you. It's a process that we use to determine the ages of things that are up to, 5,000, thousands of years old, 10,000, maybe 20,000, probably even longer if you're very careful. Oh, here I say 50,000 years. So the idea is that you can form this unstable carbon-14 by natural processes in the atmosphere. So then what happens is you have plants and animals can ingest this carbon-14 in their bodies. So you have some ratio of the carbon-14 to the other types of carbon in these animals' bodies. Then the animal dies, and this process stops, this sort of constant re-ingesting of the carbon-14 that you have. And then you just sit there, you know. And eventually that carbon-14 decays. So if you then, you know, using ratios, figure out how much carbon there is compared to, say, nitrogen 14 in these animal carcasses or whatever, these fossils basically, you can age date stuff. So you can age date organic matter this way. And this is a primary way that people use to sort of age date fairly recent civilizations on Earth, going back to some point in humanity's history. Okay, that's a bit of a digression. I just thought I'd mention it. So this concept of understanding the microscopic world in this way and these different types of nuclei and what they do becomes a source of power, really, because then it allows you to understand your environment in deeper ways. So we can use it to age date, archaeological digs, etc. But it also allows us, of course, to then understand the energy sources of the stars, which is where I'm going with this. So the simple story that I've already told you is, you back up. Now think about what we've got. The simple story is what's going on in stars is you take 4 protons, cram them together, make helium-4. There's a mass difference there, and that mass difference is what gives rise to this energy that the sun and the stars are spitting out. It's not a huge effect, right? So the mass difference you gain is 0.4% in mass compared to what you start with to what you end with. But because this E equals mc squared energy is just so big, that's enough to keep this power going. Now in practice, however, this is not really what happens. It's not true in detail that what the sun is doing is just grabbing 4 protons and just smashing them together, and all of a sudden it turns into helium. It turns out that's not a very efficient interaction at all. So what happens is you have chains of reactions that happen in the sun. So I'll just flash this to you so you see it. What's actually happening in the sun, in low mass stars like the sun, stars that are 30% more massive than the sun and smaller, okay, what you have is a chain of protons. So it's called the proton-proton chain. So what happens is, I'm reading this and I see there's a typo. I'll fix this. I haven't published these notes yet. This should not say tritium. This should say helium-3. I screwed up. So what happens is you start out with protons. You have 2 protons joined together. They fuse to make deuterium. Okay? And in this fusion process, you make deuterium. You spit out something else along the way. Now you have deuterium. Now you grab another proton. That comes together with deuterium. Then from that, you make helium-3. Turns out there's an efficient interaction. You do that twice. You have 2 helium-3 atoms. You bring those together. That fusion process, in the end, can create helium-4. So at the end of the day, if you ignore all this stuff in the middle, it's true. What you're doing is you're taking 4 hydrogen nuclei and you're creating helium-4. And that mass difference is the energy that we're talking about. But the process by which you get there is somewhat more complicated and detailed. And that's because these type of reactions are favored and more likely to happen than just randomly putting 4 things together and getting them to fuse. Yeah?
What was it spitting out again?
So there's sort of a code here. This little white thing is like an electron, except it's positively charged. So in this picture, it's called a positron. And this other thing is called a neutrino. So it's another type of particle that exists that's important for weak interactions, and it's a fundamental particle of nature. Okay. Now, the process that governs energy formation in more massive stars is different. I'm not going to test you on exactly what it is, but it's kind of interesting. So what these high mass stars do is they rely basically on different catalysts. They piggyback off of heavier nuclei to sort of eventually build helium-4. So they're doing the same thing actually in the end. They're starting with hydrogen. They're burning hydrogen, it's said. And this hydrogen burning eventually leads to helium-4. But in higher mass stars, it turns out it's more efficient to do it this way. So what you do is you have nuclei of carbon, nitrogen, and oxygen in that star that are sort of part of this chain where you build it. And it's interesting, like through the process, you know, for example here, if you start with nitrogen, you go through a process of decay and build up and gradually gobbling up hydrogen again and again and again. One of the products that you spit out is helium-4, and then you're left with the thing you started with again. And then you just keep going. So just to let you know that the point of all this is that the process of what's actually happening in these stars is a bit more complicated, and you have to understand the nuclear physics somewhat. Although in the big picture, the only thing that's going on is you're converting hydrogen into helium-4. And the steps you have to go through to get there are somewhat different depending on what the temperature is and other things, and what catalysts are available and that kind of stuff. Okay. Are there any questions about this? Okay. So going back to this kind of, one of the first questions we got here in the beginning was, do you think that we'll ever be able to build basically a little star that we can use to power our houses, right? Wouldn't it be nice if we all had just stars in the back, just spitting out ridiculous amounts of energy? We leave the lights on all the time, the air conditioner all the time, wouldn't matter. Except that we'd probably have tremendous global warming, we'd all boil. But it'd be nice to have a lot of energy, right? Because if we had infinite energy, we could pretty much solve any problem we wanted to. Well, how do stars do it? So let's figure out what are stars doing to make this happen. Well, the basic thing that you start with, we think, is then you're in some early version of our galaxy, and what's floating around? Mostly what's floating around is hydrogen and helium, it turns out. That's what we think you kind of start with. So you have this gas cloud of hydrogen and helium, and maybe you trace other things, because you probably had some previous formation of stars. And this gas, because of gravity, remember, because of gravity, can begin to contract. So gravity starts to pull the gas together into a cloud. And it starts getting denser and denser because of gravity. Now, if you start taking something just because of gravity and start contracting it, it will get denser. And if you take a gas and make it denser, what tends to happen is the gas molecules will start slamming into each other, moving around faster, and that's another way of saying it starts to heat up. What this does is it makes some pressure too, and so what you start having is you have this internal pressure, and that begins to slow the collapse of this cloud. So it's starting to the gravity now is starting to feel some pushback just from this internal pressure from the gas cloud. So you have this thing that's now getting denser and denser, and is starting to get held up to have some specific size. Now, remember what the ultimate goal here is. Ultimately, what we'd like to do, we're building our star, we want to have it turn on. So what we want to do is we want to start fusing hydrogen into helium in its core. Now, in order to fuse hydrogen and helium, what you got to do is you have to bring those protons together to get them real close together and get them to build heavier nuclei. That's what we're trying to do. But it turns out that this is not so easy. So what happens? Why is it not so easy to bring two protons together? Yeah, they repel. Okay. So more importantly, you don't even have the protons yet. Now you're just starting out with electrons bound to protons. So you have atoms. You try to bring those atoms together, they also they kind of bounce off of each other because of the electrons. But eventually what happens is if you have enough gravity, gravity will win. And the atoms will start moving around each other so fast that in fact interactions, when those atoms bang into each other, they'll knock the protons off, the electrons off. And you'll get something like a plasma. You'll get protons and electrons, like a sea of them, just kind of floating around. Everything's kind of repelling. But there's so much gravity then, you can imagine then the stuff contracts more and more and more. Now, if you're at low speeds still, low temperatures, those protons will still repel each other. They will never get close enough such that they can begin to bind. Now, the thing that will bind them eventually is this strong force that I talked about. In principle, once you get those protons close enough together, the strong force can take over, bind them together, it becomes very powerful, then you can start building nuclei. But you got to get there first. You have to overcome that Coulomb barrier, that electromagnetic barrier, to get that thing to happen. And the only way you can do that is you got to squeeze them hard, you've got to get them going really fast, which means a really high temperature. Okay? So the core of the sun is very hot. The core of something massive has a lot of pressure. It gets really hot, and you can drive all this stuff together. Okay? So the nuclei can get close together, and fusion begins to happen. So that's the point. You have to put in a tremendous amount of energy and pressure to hold this stuff tight together to create that fusion, to get it to happen. Now, the interesting thing begins to happen now, right? So now you start to get this fusion. This is just what I just said. I'll leave it up here. I'll put this in the notes. You can read it yourself. That's just what I just said. So now what happens, right? So now what happens is you've got this region in the middle of this star where it's got to be so hot that fusion has started to happen. These protons are going through these chains, eventually creating helium-4, generating energy. Energy's coming out. Now what does this energy do? Effectively what it does is it heats the stuff up now even more and applies more pressure. So what happens is you push things together and then all of a sudden that makes it explode a little bit. You can think of it that way. Okay, so imagine you're cramming things together so much, but when you get them real close, they sort of pop and then explode a little bit. So if you were trying to do this by hand and it popped, it wouldn't be dense anymore. So now it would stop. So you had just enough pressure to make this stuff explode, and now it explodes, and then it doesn't explode anymore because now the pressure's released. Well, then you squeeze it again, and more start going off, and then it breaks up again. So what happens is you reach an equilibrium point where just enough energy is coming out to balance that pressure from gravity pushing in. And you reach a steady state. Because if you squeezed it harder, you would have more of these interactions, more energy released, and that would push you back out again. But if you squeezed it more lightly, then the interactions would turn off completely, and you'd have less pressure pushing back on you, and you could squeeze it more again. You see what I mean? So it's a competition. You end up with a competition, an equilibrium between gravity pushing in and basically the energy release pushing out. And there's no choice but to end up with a steady state. This kind of very regular steady state reaction. Okay? So that's why the sun isn't just like this bomb. Like it's not just like and then gets dark and then for a while and then it gets light again. It's set up to be in equilibrium. Okay? That's the natural state for it to be in. And it turns out when stars are in this state, they're said to be on something called the main sequence. The main sequence of stars is stars that are living in this steady state. And stars live most of their life in this steady state. All right? And the sun right now is in that part of its life. And that's good for us, right? You want your sun to be pretty steady. You want to count on the sun. Right? You want the sun to be spitting out about the same amount of energy all the time. If it was if it changed a lot in how much energy was coming out over time, that would not be so good for us. It'd be hard to plan your day if that was going on, right? Of course, in reality, we probably wouldn't be here. Are there any questions about that? Yeah.
So when you're explaining like gravity brings the atoms together to like come together, but then wouldn't there be like strong force or like force like have that short?
So the strong force is what eventually makes the fusion happen, you could think of it as. So gravity is so strong that it overcomes that electromagnetic repulsion. So that's a very different situation than is even in the center of the Earth, right? There's a lot of pressure from gravity and stuff at the center of the Earth, but it's not high enough to make fusion happen, because you got to really cram that stuff together to get the fusion to happen, right? And so you have to have a lot of gravity for that to happen. And then what that means is you're bringing these two protons together that really want to repel each other because of electromagnetic forces. But you get them close enough together, and only when you get them close enough does the strong force act. One of the weird things about the strong force is it only acts on very, very small scales, very tiny little scales. And so you have to get these protons really close together before the strong force takes over. So the strong force is there and matters, but only when you cram stuff really close together. So that, in some sense, that's why fusion is hard to why it's hard to make it happen. Does that make sense? Okay. Any other questions? Here's a picture of some stars that were recently formed. You know, recently for an astronomer, right? Much younger than our sun. This is a very famous star cluster. It's called the Pleiades. All right. If you recognize the stars here, this is Subaru, right? It's the same constellation. It's a very famous constellation. But this is a star cluster. We think that stars actually tend to be born in clusters. They aren't born singularly. They're born kind of in big clouds, and within those clouds, stars form. And this blue light, as I'll talk about next time, this blue light coming from the stars is a signature of young stars. Young, massive stars burn very hot, and therefore they burn blue because of the law of black body radiation. You might ask, okay, where does it stop? So I talked about how you need all of this mass to get stuff crammed together so much that fusion takes over. And I was talking about how, well, that doesn't happen in the Earth, which is kind of good. You know, you don't really want like a sun, and we don't want to be standing on the sun. So where does it stop? You can imagine that there's some things, these massive bodies that collapse, that at some point they're just not massive enough to make nuclear fusion happen, and then they stop shining. All right. So, and let me, before I get to this, I just wanted to mention this too. What tends to happen around these stars is most of the mass concentrates to this star that we're talking about. But there's stuff that's left over that doesn't get incorporated into this main engine. And what that does is it tends to orient itself in a disk. And I'll talk about how this is a general phenomenon later. It turns out that if you have stuff that has any angular momentum, that's a quantity in physics that matters, you tend to, in gravitationally supported things where gravity matters a lot, you tend to create disks of material. And what we think eventually happens in these disks is you get little overdensities that begin to collect, and they create less massive bodies that then orbit around the primary thing. And eventually those things are what become planets. So, and we think solar systems are born at about the same time as the stars are born, more or less. And eventually they evolve into these, more stable systems with planets orbiting around. In the very beginning, it's kind of chaos. There's rocks flying everywhere. It's sort of crazy outside of a new star. But eventually things settle down, and you create these more stable planetary systems. So where does it end? I was saying, the Earth is not massive enough to have this nuclear fusion. The sun clearly is. Where does it end? it turns out that they end with things called brown dwarfs. So brown dwarfs are kind of failed stars. So it turns out about 8% the mass of the sun is the limit, more or less. So if you're more massive than 8% the mass of the sun, you can basically be a star. But if you're less massive than 8% the mass of the sun, or 80 Jupiters, okay, so 80 times the mass of Jupiter, you can no longer be a star, and this is called a brown dwarf. That's what a brown dwarf is. It's like a failed star. It's not big enough to burn on its own, to burn helium on its hydrogen on its own. So, you know, the Jupiter is kind of a little brown dwarf. You could think of it that way. And the sun is, you know, more than 10 times massive than a brown dwarf. Okay. So, are there any questions about that? Yeah.
So, in order for the nuclear fusion to happen, it has to be like really, really big.
Yes, exactly. So, thank you for getting me back to this point. So the point here is that in order for this nuclear fusion to happen, you need to be really massive. Have enough mass so that you can squeeze all this stuff together to get this fusion to happen. Okay. Coming back to the original question in class, which was, why is it so hard to build a fusion reactor, right? So the question is, what are you going to do? How do you do it? How do you take these protons and hold them together so closely that then they create the fusion? Then let's say energy comes out. Well, then what do? How do you push them back? Okay, you can't use your hands to do that because you'll get burned. You know, these are plasmas. It's really hot. So you got to build some kind of container. Well, imagine trying to build a container that did this, right? The walls would get blown apart. So in practice, what's done is you use magnetic fields. So it's a technology that involves really strong magnetic fields to confine matter in such a way that you create this fusion. And you know, the easiest thing to do is to make a bomb out of it. You set things up so that it happens, and then it just explodes and blows everything up. And then you build a new one, and it explodes and blows everything up, right? That's kind of easy compared to what you really want to do is you want to have something you can control. Okay, you want to put fuel in of some kind. The thing just starts making energy by fusion. But the way the sun does it is it just has so much mass that it's not an issue. It's just using gravity, right? But you obviously can't build that. You can't build something as massive as 8% the mass of the sun, right? That's not going to work. So instead, we have to figure out another way to create these conditions without using gravity as our force. We have to create some other way to use it. And again, it takes energy to build these magnetic fields and cram things together. And at the end of the day, we can get fusion to occur. We can make new matter in the laboratory. But what ends up happening is you have to put more energy in than you get out on average in the long run. So then it's not very useful for an energy creator, right? So finally, I've answered your question, sort of, hopefully. So anyway, all right, that's it. Homework's due tomorrow. We'll see you Tuesday.